I hope everybody is refreshed and recharged because now it's time for the hot side. So Jonathan, let's get going on hot accretion, physics of hot accretion and cooling flows. And Jonathan managed to, yes, Jonathan managed to escape from Chicago to Israel. So he himself has gone from very cold to what I would consider hot. So speaking to us from a warmer climate, Jonathan Stern.
Thanks, Mark. So thanks everybody for joining. I would like to very much kind of thank the organizers for this amazing conference, which really has managed to put so many great people together, and I'm really enjoying the discussions and I'm really learning a lot. So really thanks for that. You can hear me well? Sorry.
Yes.
Yeah, okay, good. Okay. Okay, so I want to kind of give this tutorial about cooling flows. Cooling flows is a subject which has been discussed extensively in the literature of the ICM, of the intercluster medium, but it's actually hardly been discussed in the context of the circumgalactic medium, in the context of the CGM. Okay, and kind of bridging this gap between the different kind of emphases between the two communities is one of the main goals of this tutorial. Okay. And the way I want to do it is, so just kind of a quick outline of my talk. I just want to first just quickly go over naming conventions, just so everybody's on the same page and what I mean when I say a cooling flow. Then kind of briefly address I think the main observational question concerning cooling flow is that, is there a cooling flow problem in galaxy scale halos? I'll then review a basic theory of cooling flows. Okay, that's something that's kind of been developed extensively in the 1980s, again, mainly in the ICM literature. And I'll end with something which is a relatively new result about the theory of cooling flows with angular momentum, and specifically how do cooling flows accrete onto the disk. Okay, and I put a teaser here, if you'll remain to the end of the tutorial, that the answer depends qualitatively on halo mass. Okay, so let's start. So first, naming conventions. Okay, so first, when an ICM expert says a cooling flow, I mean somebody like Pratik Sharma or Mark Voigt, okay, he means something like this. He means that the whole hot halo is inflowing towards the center of the potential well. Okay, now the gas is relatively cooling, so that starts an inflow. Okay, but as it's inflowing, it's being compressionally heated, and this compressional heating roughly balances the radiative cooling. Okay, so in a cooling flow, in these classic cooling flows, the gas temperature actually remains roughly constant, and the gas is only losing entropy. Okay? So since eventually what's being radiated is gravitational energy, the inflow rate kind of in these kind of classic cooling flows is the luminosity over the difference in gravitational potential. Okay, so that's what I call a classic cooling flow, and that's what ICM people say when they mean what I mean when they say a cooling flow. In the CGM literature, I've already seen something like this called a cooling flow. And this is kind of the general flow of gas in temperature space from high temperature to low temperatures. Okay, kind of without specific sublocation. I've seen a lot of discussion of this, for example, in Matt McQuinn's and Jessica Welk's paper. And this is also called a cooling flow, but it's something else. Okay, this is gas which is actually cooling. It's actually losing thermal energy. And therefore, the inflow rate through the flow in temperature space is the luminosity divided by the difference in specific thermal energy. Okay, so I've seen also this being called cooling flow, but this is something very different from kind of these classic cooling flows. Okay, so it's just kind of very important when you read about something to understand which one of these this is, and of course, if you like, to be kind of specific what you mean. And of course, there's also cold flows, which have a similar name, but a very different thing. And this is, of course, what Neil discussed. Okay, these are just gas flows which are roughly at the equilibrium temperature, and they're free fall. Okay, the mass inflow rate is roughly the mass divided by the free fall. Okay, so kind of similar names, but very different things. Okay, so cooling flows is essentially a type of hot accretion, and cold flows are, of course, a cold accretion. Okay. So that's just to put kind of order in the naming conventions. From now on, all I'm going to talk about is the classic cooling flows. okay, what the ICM people call cooling flows, and I'm just going to call them cooling flows, okay? Okay, so before I reach the cooling flow problem in the CGM, I want to just briefly put everybody on the same page on what is the cooling flow problem in the ICM, okay? So basically the idea of the cooling flow problem, which is a 40-year-old problem, is that if you look at the X-ray emission from the ICM, you assume it's in a cooling flow, you can derive from the X-ray emission what is the inflow rate. And then if you compare this inflow rate to the star formation rate in the central galaxy, they're different by between 1 and 2 orders of magnitude. Okay, so you're seeing gas, which is relatively cooling, which implies a huge inflow, but then you don't see this gas piling up or forming stars at the center. Okay, so the immediate consequence of this is that the gas is not actually inflowing, and there's some heating term, potentially by AGN feedback, which is kind of replenishing the energy, the gravitational energy lost to radiative cooling. Okay, and our kind of standard model for the ICM is called a thermal balance model, and the reason is because you have to assume that the heating of the ICM roughly accounts for all the cooling. Okay, because the amount which actually forms stars is such a negligible amount of the total cooling. Okay, you need the heating to entirely compensate for the cooling. Okay. So that's the problem in the ICM. One kind of anecdote, which is not the focus of this tutorial, is that not all clusters have a cooling flow problem. Okay, if you look, for example, on a Phoenix cluster, which is the star on the top right of this figure, okay, its inflow rate suggested by the X-ray emission is actually comparable to the star formation rate. And actually, if you look also at other properties of the ICM, they also resemble cooling flows. Okay, so if we want, we can discuss that further in the discussion. But at least most galaxy groups and clusters are inconsistent with cooling flows and require some kind of thermal balance. So that's the ICM. What about the CGM? Okay, so this is a similar plot for the CGM. Okay, so around the X-ray emission around L-star galaxies. Okay, so around L-star galaxies, it's much harder to see the X-ray emission, but it's still possible for a few local bright sources. And this is a compilation by Jingtao Li. And basically what he did, again, he took the extended emission around local L-star galaxies, calculated from that what is the expected inflow rate if you assume they form an inflow, and compare that to the star formation. Okay? And the dashed line here is the one-to-one relation, but notice that the axes here are inverted relative to the previous plot. So here the star formation rate is on the horizontal axis, and kind of the expected inflow rate is on the vertical axis. Okay, and the situation here is very different from in the ICM. Okay, essentially you can see that the star formation rate is comparable or even larger than the inflow. Okay, so there's no direct evidence for a cooling flow problem in L-star galaxies as there is in kind of galaxy groups and clusters. Okay, the X-ray situation is very different. Okay, so another way to put this, okay, essentially is that if local L-star galaxies had a cooling flow problem, their X-ray emission would be much brighter than actually observed. Okay, their X-ray emission would appear kind of on the top left part of this plot, and they would be much more brighter in the X-ray than we actually see. Okay. So at least my conclusion from this is that thermal balance is not required by the data, by the X-ray data, and we should consider the possibility that the hot CGM, okay, the hot phase of CGM is actually inflow, okay, because we don't have kind of a strong reason to believe there's thermal balance. Okay, I'm not trying to say that thermal balance in the hot CGM is ruled out, but it's definitely not required by the data. Okay. So just kind of to put this conclusion in the context of this cartoon that everybody likes to use as a punching bag, my point is that kind of this diffuse phase, okay, this volume filling hot phase in the CGM, okay, is potentially inflowing and feeding the disk, okay, not condensing and then cool clouds feeding the disk. The whole hot volume filling phase is inflowing and feeding the disk. Okay, we should
Is everybody else seeing Jonathan frozen?
Yeah.
80s by the, yep. Yes.
Jonathan, you froze at a crucial moment. You were saying that the whole diffuse halo is inflowing, not condensing into cold clouds, and then you froze in this very emphatic pose. So maybe you can go back and keep going.
Sorry, was that here? Was that on this slide?
That was on this slide, yeah. Right at the beginning, it was absolutely. I was riveted, and then you just froze.
Yeah. Right after you said this cartoon is a punching bag.
Okay. So first, just to be clear, I'm not saying it's necessarily inflowing, okay? But I'm saying we should consider the possibility that the volume filling phase is kind of inflowing into the center. Okay, I think that scenario, which is kind of ruled out in the ICM, is definitely not ruled out in the CG. Okay, that's my main point. Okay. Great. Okay, so that was kind of the that was kind of the background. Wait, let me just so I see I don't freeze. Okay. Now I see Jessica, and then I know I'm not freezing. Okay, great. Okay. So now a little bit about the physics of cooling flows. Okay, so I hope I can kind of convince you that it's at least possible that the hot CGM phase is inflowing and feeding the disk. Okay, now you can ask the question, what are the properties of this hot CGM if it is inflowing? And this is something, again, that has been discussed a lot in the context of the ICM, mainly in the 1980s. What I did together with Drummond Fielding is kind of adapt the results that were derived in the 1980s for the ICM for the CGM, for the hot CGM, okay? So this plot is a plot for my paper. It basically demonstrates some of the expectations of a hot CGM, which forms a cooling flow. Okay? So what you see on the left is kind of snapshots from Drummond's idealized CGM simulations. Basically, we assumed a hot halo. Sorry, we assumed a halo potential and put inside gas, which is hot and initially hydrostatic, and we just let it radiatively cool, and then it formed an inflow. Okay, and you can see here snapshots from different times in the simulation. On the left, you see temperature, and on the right, you see inflow radiated velocity. And you can see that the gas it remains hot, and it forms kind of a very mild inflow. So can you see my cursor? Okay, great. Okay, so if you look, it looks, for example, on the M dot. Okay, these are profiles for kind of radially average profiles. Each solid line is a different time in the simulation. In the initial, there's no inflow. The initial conditions are static. And you can see that after some time, you get kind of this very mild inflow, roughly 1 solar masses per year in the simulation. Okay, the velocities are very slow. It's only like 20 or 30 kilometers per second. The inflow is very mild. It's very subsonic, so much lower than the sound speed. Okay, but the point is because there's so much mass in the hot phase, okay, this inflow could be significant for feeding the gas. Another result here you can see is that the temperature remains roughly at the virial temperature. Okay, so this is what I showed you before, that the gas is cooling, but because it's inflowing, it's being compressionally heated, and these two roughly compensate for one another, and therefore the gas remains hot. Okay, and the third property, which is kind of probably the most important property of cooling flows, is that the flow time, R over the radial velocity, it roughly equals the cooling time. Okay, so again, in the initial conditions, the flow time is infinity because there's no velocity, but very quickly you reach a solution or reach a scenario where the flow time equals the cooling time, and essentially the gas reaches the center on the cooling. Okay, so that's kind of a very basic description of what cooling flows do, and that's been discussed a lot in the ICM. Yeah, okay. So I kind of put here a few more properties of cooling flows. I'll just kind of briefly mention them, and I think if you want, we can discuss them further in the discussion. So first, the formation time of a cooling flow is the cooling time. Okay, so if you think you have some kind of burst of feedback, some strong heating effect, okay, which kind of stops the cooling flow, you can ask the question, how much after how much time the cooling flow reforms. Okay, and that actually turns out to be a very short time in the inner CGM, where the cooling time is only something like 300 megayears. Okay, so if you have a Bilstein feedback scenario, okay, then you will have kind of a cooling flow being reformed again and again and again. Okay, so it's very reasonable, especially in a galaxy like the Milky Way or similar disk quiescent galaxies, that at least the inner CGM is forming a cooling flow. Another important thing is that the flow is very subsonic, as I said before. Okay, that means that the pressure profiles of our cooling flow are very close to hydrostatic. Okay, actually, to the first order, they're actually hydrostatic. Another thing is that the thermal instabilities, which grow on a cooling time, are advected also on a cooling time in a cooling field. Okay, so thermal instabilities in a cooling flow don't have time to grow because they're advected on the same time scale that they're growing. Okay, so generally, if the hot phase forms a cooling flow, okay, we don't expect it to kind of naturally form multi-phase gas. Okay, we expect multi-phase structure only near kind of these large disturbances like satellites or filaments or the disk. Okay, kind of the volume filling phase should not be multi-phase. And of course, there's this prediction for observations that the density scales roughly as r to the minus 1.5, which means a beta parameter of 0.5. So this is a prediction which can be compared to X-ray observations. Okay, so that's kind of generally cooling flows without angular momentum, and this is all kind of relatively old stuff. Just we kind of applied them to the CGM, and I think there's a lot to test in CGM studies using these results. And that's the last part of the talks. What happens to cooling flows when you add angular momentum? Okay, and this is based on recent work that I did together again with Drummond Fielding. So we have hot gas which is inflowing, and in a cosmological scenario, this hot gas should have angular momentum. Okay, so at some point when the radius becomes small enough, angular momentum support should be significant. So what happens in these kind of, when you assume angular momentum, is that the hot flow kind of stalls at the angular momentum radius and kind of converges onto the disk. Okay, so what you see in this plot is, again, this is a snapshot from Drummond's idealized CGM simulations. You're seeing here the flow lines projected on the alt theta plane, where the gas is actually rotating in the phi direction. Okay, this is the plane of the disk here at theta equals pi over 2. And you see that the flow is kind of radial at large scales, and then it just converges onto the disk. Okay, so what the angular momentum does is that it essentially stalls the cooling flow. Okay, the cooling flow could have, in principle, just continued to flow inward into smaller and smaller radii, but because of angular momentum, it will stall here and immediately cool onto the disk. Okay, so if the hot CGM forms a cooling flow, it suggests that the inner hot halo is rotating, okay, roughly at the circular velocity, and that's consistent actually with observations of the Milky Way hot halo. Okay? Another interesting question is the fact that the gas. Another interesting point is that the gas cools just before it joins the disk. Okay, so that might have interesting predictions for extraplanar H1 or for HBCs. That's something we need to look into more. And one more point I want to make is that this is the dominant accretion mode in the fire simulations of Milky Way mass halos at low redshift. Okay, so this is definitely how kind of Milky Way mass low redshift halos accrete in fire, and that's kind of a paper that Zach is leading, which is still in preparation. Okay. Okay. So just kind of to put this in context of other models for rotating hot corona. Okay, so this is something that came up a lot in this conference, and I'm very glad. Okay, that there's kind of been several kind of people look into the fact that the hot halo of Milky Way-like galaxies is rotating. So first, there's the observations. Okay, this is this phenomenological model by Edmonds based on the kinematics of O7 absorption through the Milky Way hot halo. And he actually deduced that the hot halo is likely rotating. Okay, so first, kind of very strong observational evidence. Then there's these hydrostatic models by Matthias Sormani. Okay, so basically what they assumed is that the hot halo is rotating, but it's static. It's not inflowing like in our models. What you see here is essentially profiles of specific angular momentum in their models. These models are actually pretty similar to our models, or our models are similar to their models, because, as I said before, because the inflow in our models is very mild, very subsonic, the pressure profiles are very close to hydrostatic. Okay, so essentially our models form a kind of subset of the Storm-Money models. And of course, there's also evidence for hot halos rotating, also in kind of Illustris and in Eagle. Okay, so this is a paper by Ben and from the Philippus in 2020. Okay, how much time do I have?
Well, try to wrap it up in a few minutes, so
Okay,
we can have good time for discussion.
Okay, so I have one last. Okay, so one last point. So I won't jump into 5 minutes. And that is, how do the cooling flows depend on halo mass? Okay, so what happens in these cooling flows is what you get from, if you look at the cooling flows, that the ratio of the cooling time to free fall time decreases inwards. Okay, so if you have a perfectly radial cooling flow, at some point at some small radius, the cooling flow will drop below the free fall time. Okay, and once the cooling time drops below the free fall time, compression can no longer compensate for the radiative cooling. Okay, so at some point, the hot gas will essentially turn into a cool supersonic flow. Okay? Now, in massive halos, kind of the cooling flow reaches the angular momentum radius before it reaches this point where the cooling time equals the free fall time. But when you go to low mass halos, okay, the transition between kind of a subsonic hot inflow with cooling time larger than free fall time to a supersonic cold flow with cooling time shorter than free fall time happens on the CGN. Okay, so cooling flow in relatively massive halos kind of gently settle on the disk with a subsonic flow, while in low mass halos, these subsonic cooling flows first turn into supersonic cold flows and then crash into the disk. Okay, so they go through a sonic point and then crash into the disk. Okay, so there's kind of a qualitative difference between how cooling flows work in Milky Way mass halos and in lower mass halos. Okay? And I'll just kind of make quickly the point that we identify this transition in the fire simulations, and this transition between kind of these transonic cooling flows to subsonic cooling flows is associated with the suppression of supernova-driven outflows in fire. And I'll end with that, okay? And maybe I'll just leave my summary here.
Okay, thank you very much. I will applaud live, and we'll. There's some questions already accumulating in the Slack, and I will also look for hands in the Zoom chat. I see there's a question from Jess that says, for the cooling flows, the models seem to also predict velocity and temperature profiles, correct? And it seems like at 100 kiloparsecs and beyond, the temperature is a few times 10 to the 5th, question mark?
Yes, so the cooling flows predict very clearly what is the temperature profile. It's essentially equal to the gravitational temperature, what Mark called the gravitational temperature in his tutorial a few weeks ago. It's roughly the virial temperature, or roughly, which is proportional to the circular velocity squared. At 100 kiloparsecs specifically, the cooling time could be very long. So it depends on, right, the cooling flow kind of applies only where the cooling time is shorter than the Hubble time. So it's kind of questionable at 100 kiloparsecs. But generally, yes, you can tell from a cooling flow solution what is the temperature at each radius.
Okay, and Todd Tripp has asked a question that has received a bunch of replies there already, which is, why is low ionization gas, including a variety of metals, found at large impact parameters with high covering fraction?
Yes, that's a great question. Yes. So first, when you say large impact parameters, right, it kind of, the question is, what, when you say large impact parameters, what do you mean? Okay, so if it's gas, then some of the gas comes beyond the accretion shock, and there, I think, there we expect cooling gas. The cooling flow kind of only happens within the virial shock, and I think it's kind of a question where the cooling flows are. But I guess it could be also, could be satellites, could be anything. If it's a cooling flow, cool gas won't spontaneously form. Okay.
Okay. Bill Brakeman has hand up.
Yeah. Let's see. Yeah, I'm unmuted. So some of the things that were suggested, in the various years about cooling flows, was that there would be enough in the way of disturbances, that there would be thermal instability that would grow at large radii, because the mass loss from dwarfs or stars or inflow would lead to such behavior. And that doesn't seem to be present in what you show. So is that just too much microphysics, or could you elaborate?
So I'm not sure, Joel, I understood the question. So
yeah, so when people were doing, so it looks like the cooling rate certainly is the radiative rate, but you can have thermal instabilities within the condensations, as Mark well knows, within the cooling radius, which is twiddle 100 kiloparsecs, right? But it looked like the simulations that you were showing didn't seem to have those. So
definitely, if you have a very pure cooling flow, okay, then you don't have any sources of kind of older unity density fluctuations, then they won't naturally form. Okay. Now there's this question about the low ionization gas. How we see in observation, how does it form? So it can form due to near the disk. It can form due to filaments. It can form due to satellites. Like as Domen discussed, there's many reasons where these instabilities can form. Okay. My point, I think, for the cooling flow is that they should not, these ionization, these low ionization gas should not be volume filled. Okay. So I think what Todd Flip said, that the coupling factor is very large, that still does not tell us that the low ionization gas is volume filled. I think it still could be confined to relatively reasonable regions in the halo. It's not definitely kind of like Milky Way and more massive galaxies, definitely at large impact parameters. I don't think we have evidence that you have cool gas everywhere. Okay, we know there's a large area covering fraction, but that still doesn't tell us what the volume filling fraction. I would say that observations, such as Catchflex observations, which show that low ionization gas is maybe more along the minor axis, major axis, and less like in intermediate angles, that actually suggests that you don't see low ionization, that there's not cool gas everywhere. That's only near disturbances like the disks and alpha.
I guess I was asking you to reconcile the models you showed with that of Juan Lee and Mark Voigt, which seemed to be somewhat different and somewhat more complicated in terms of the radial distribution of cooling material.
I guess I could comment. So I think observations show that at some significant height, T cool is longer than T free fall in the volume filling phase. And if that's like very dynamically quiet and undisturbed, you don't expect thermal instability to progress. But if there is some disturbance, then you can get condensation to happen. So in an idealized simulation, you don't, that gas stays single phase until you cross into the region where T cool is less than T free fall. but as we see in cosmological simulations, there are many different forms of disturbance that could cause the gas at larger altitudes to be multi-phase, even if T cool is longer than T free fall. Is that the parsing you were looking for, Joel?
Yeah, because the distributed cooling lowers the cooling crisis that you show, where within 30 kiloparsecs, things catastrophically cool. And it's not obvious that one sees that. But
not in Milky Way mass halos. The catastrophic cooling will only happen at lower mass halos. Now, in Milky Way mass halos, the gas will remain hot kind of down to the disk.
Yeah, I'll just add one other thing. I mean, there's been some comments about the temperature of the volume filling gas. When we look at galaxies, both elliptical and spiral, the gas temperature is usually about 50% higher than the virial temperature. And actually, that would be needed. As you raise the temperature, the value of beta decreases, and you would need a hotter temperature to have a beta of a half gas. So, Milky Way type galaxy, 2.4 million degrees is the mean temperature that's seen, yet the virial temperature is, 1.4, 1.5 million. And that's very typical.
I mean, it's definitely the quality with the virial temperature is rough, right? And all the unity factor is definitely reasonable in these.
Yeah, and technically it depends on the pressure gradient. But let's move to a question, Jiangtao Li.
Okay, thanks. This is a very nice talk. Well, my question is mostly based on related to the role of feedback in these cooling flows. So I just wonder, as you show in massive galaxies, the inflowing gas is keeping hot. So I guess in this case, the feedback may not be very efficiently heating the inflowing gas. So it may not have really important effect on the inflow. But in low mass galaxies, as you show, the inflow can become supersonic and the gas can cool. Well, in this case, I just wonder, will the feedback play a role in heating the inflowing gas and finally turn it back to an outflow?
Yeah, so I can tell you what happens in the fire simulations, right? So in the fire simulations, like when we're in this low mass halo regime where the cooling flow at small scales turns into a supersonic cold flow, you have lots of very strong feedback, very strong outflows. And this kind of outflows, they both kind of mix with the inflow cooling gas, the cooling inflowing gas, and they also affect kind of the hot gas at larger radii. So yeah, it definitely has an effect. It also kind of creates these instabilities. There's definitely feedback. I think kind of, the main advantage of the cooling flow is that it's the baseline state of the hot gas. Okay, if you think about like what happens in a disk, like the Milky Way is quiescent. Okay, and if depending on how much. And assuming that AGM feedback is not kind of super much heating the CGM, then you would get a cooling flow. Okay, any deviation from a cooling flow would be due to feedback. Okay, and the cooling flow I think is a very useful as a baseline
caused by star formation feedback because we are talking about the low mass galaxies, right?
Yes, in low mass galaxies, yes, and I guess my point is that these kind of models, these cooling flow models, are very useful as a benchmark for how the hot X-ray CGM behaves. Okay, so any deviations would be due to feedback or due to other complexities kind of in cosmological simulations, but they give you kind of what is the zero order behavior you expect for the hot CGM. And we should compare our observations to these models and to understand where these models work, and that means that feedback is not very strong, and see where they don't work, and that kind of suggests that feedback is strong. Okay, that's kind of, I think, the main point I'm trying to make.
Oh yes, I just guess maybe in the relatively inner halo of the CGM. So what you have seen is probably dominated by outflow instead of inflow, but at larger radii, maybe inflow dominate.
What do you mean dominated by outflow or inflow? I mean, in
I
these
mean,
simulations,
what you
there's
see
no
is
outflow.
the gas is mostly just outflowing. For example, typically within a few tens of kiloparsecs from the galaxies.
Yeah, I'm not sure to what are you referring to. In these simulations that I showed, these kind of ideal simulations, there's no outflow. Everything is an inflow. Okay. In fire,
okay.
we have kind of in the indoor CGM, we have a mix of inflows and outflows.
Okay. Okay, thanks.
I'm sorry, I think I was muted. Rosie Talbot from the Slack asks, do you expect magnetic fields will alter the picture significantly? Would it change the angular momentum of gas that reaches the disk?
That's a great question. Yeah, I mean, what happened? Yeah, that's, if anybody else wants to answer that, I'll be glad. I mean, basically, I think, as you're inflowing with the magnetic fields, they will become stronger at smaller radii. But what would be the exact effect? That would be a great thing to study.
Mitesh conveniently has his hand up.
I could comment on this, but I was going to ask a different question actually. I want to come back to what Joel asked and whether there is a full consistency of the result with, let's say, Yuan Li's results or anybody else's who simulated thermal instability on these inflowing blobs. So, as far as I understand, but Jonathan can correct me, these idealized simulations don't include any heating sources, right? It's just cooling and rotation.
Yes, exactly.
And so in that case, I think standard or classic result by Balbus 1988 applies.
Yes.
And what was demonstrated in that seminal paper is that you don't actually expect any fragmentation and instability. Basically, standard isobaric instability is not expected to occur, and that's fully consistent with what you're seeing in your simulations. So if you
it's advected. So just to kind of be clear, it's advected, right? So until they grow, they're already advected kind of towards the center. Okay, it's not
right.
that there's no the gas is still unstable, but it doesn't have time to grow until it goes to the center.
Right.
But sorry for interrupting.
Yeah.
Yeah.
And actually, since I have the floor now for a second, so about that other comment related to magnetic fields, I think they will make a huge difference, and we've seen this, for example, in Charan Wang simulations where magnetic fields get selectively amplified at the locations of condensing gas, and even though you start with very high plasma beta parameter, you end up selectively amplifying fields right where the blobs are, or right where the condensing gas is, and the impact can actually be severe, and you can get rid of any disks would otherwise produce or get generated in the center of these potential wells. So I would expect the impact to be very significant in an interesting way. So that's just a comment.
Okay, and maybe Frika has
yeah, I'm not sure. So we have done this experiment, and so have others. Joe Whittingham has recently also put out a paper, and both of these works find that so with magnetic fields we end up with much more extended stellar disks. So if you study the galaxy, so I mean there's Zoom simulation, so it's not infinite statistics, but we now have like about like a dozen examples where the hydrodynamic simulations have a smaller disk with a very strong cutoff, sort of where the gas disk ends, and also, I mean, that has consequences for the stars that form from this gas disk, of course, and for more extended stellar disks, and then depending on how you define, your disk to total ratio. So my work found that the disks are more prominent, so a higher disk to total ratio, but there's also other kinematic ways of determining what your disk is. So Whittingham et al. Found that they are fairly similar in their disk to total, but still different in their extent. So I would say that magnetic fields are likely to increase the angular momentum of the accreting gas.
Thank you. So Yuan has a question in Slack and her hand up. How does the hot gas join the cold disk exactly? Does turbines in the SM scoop up or down the hot gas and mix whole cafes? Yuan, is that a question you still would like to ask?
Yeah, but maybe I can make a comment first, just to add a little bit to what Joe raised and what Mateusz said. And I totally agree with Jonathan and Mateusz. So even if you do a ICM simulation without perturbations, you will just have a pure cooling flow that's thermally stable, and cooling will only happen in the very center. And maybe another way of looking at this, and I think Drummond Fielding also pointed that out, and this is how I looked at it at least, so in my first paper in 2012, I looked at the cooling time and the heating time due to compressional heating time. So as the gas flows inward, it gets compressionally heated, and that perfectly balances cooling in the classical cooling flow. So you only develop thermal instabilities when you start perturbing this halo. But I would also like to add that even in the cases where you think there's a lot of heating, for example, in the ICM, one can still view the hot phase as being, well, in a reduced cooling flow. And this was also nicely pointed out in Karen Young's paper, I think maybe with Mateusz, where she looked at the part where the jets are not heating directly. So you can basically call that a cooling flow. So the gas is still flowing inwards, and you can have regions that are not developing local instabilities. Oh yeah, and I have a question on Slack about how exactly the hot gas joins the SM.
So kind of at least, this is something we're still looking into, but at least what we're seeing both in the idealized simulations and in FIRE is that just before it joins the disk, it cools out. Okay, so the compressional heating kind of continues just until a few scale heights, and then everything kind of cools together. So hopefully we'll have kind of more quantitative results, but it should be some kind of cool gas above and below the disk, okay, which is inflowing towards the disk.
So does it cool over a cooling time, or does it cool more quickly? So if it's due to mixing, then you have cooling like that. If it's just cooling because of radiative cooling, then it would cool over cooling time. So you use a particle-based code. You can look at that.
So first, Dolman simulations is actually a grid code, but the cooling time is super short, right? Because we're talking very close to this. The gas is very dense, okay? So it can cool very, very quickly, and it even becomes denser because it's rotating, so it's not spherically symmetric. So it should be some kind of cool gas, which is, right, so it's hot. It's a hot inflow down to maybe 10, 15 kiloparsecs, which then turns into a cooling inflow onto the disk. That's kind of the picture.
Thank you.
All right. As Greg Bryan asks in Slack a question which I might have asked myself, which is what sets the mass accretion rate in the cooling flow? Because in the absence of feedback, a cooling flow in a regular cosmological accretion would have a much larger magnitude.
Excellent. Yeah, so thanks for the question. So basically there's one free parameter in these cooling flows, or let's say two free parameters. One is the gas metallicity and the CGM metallicity and the total CGM mass. Okay, so for example, if you think about low redshift Milky Way mass halos, okay, their metallicity and their mass are probably set by feedback at higher redshift. Okay, once those are set and you know these two parameters, then you can kind of predict what is the inflow. Specifically, for example, to get an inflow rate such as what Joel Bregman measures in the Milky Way, you need the hot CGM to be maybe 10 or 15% of the baryon budget. So lower than kind of a baryon complete hot halo.
Okay, so this, yeah, whatever sets it has already happened by the time your model comes into play.
Exactly. Yes.
Mir. Yeah.
So I guess I was wondering, Jonathan, what your thoughts were on how we might be able to, well, I guess two questions. One, how we can observationally perhaps distinguish them, and two, what might the difference be in terms of the accretion onto the galaxy and subsequent star formation between cooling flows, which you know I think we would all agree are likely more dominant, at least on average, at low Z, as opposed to the cold streams, which are at least theoretically on average more prominent at high Z. But how can we really, or can we really tell them apart observationally, and what might the different effects on galaxies be?
Yeah, so one big difference, you know, which you guys talked a lot about, is kind of the turbulence induced in the disk, right? So in these subsonic cooling flows, right, everything is subsonic, causally connected, okay? The inflow knows that the disk is coming, okay? And so it's a very gentle kind of settling on the disk. And then when you have these streams, or even when you have kind of these cold, you know, the spherical cold flows, right, then everything is supersonic and not causally connected, and it would, you know, much more increased turbulence in the disk. So at least in fire, when we see this transition kind of between cold flows to kind of the subsonic hot accretion, the disk becomes much thinner and it becomes kind of much less turbulent, a much more thin disk. Yeah, so that's, I think, kind of the main effect.
Okay, so there's a question in Slack from Huanyan Zhang, where the first part, I think you've answered, but the second part is, how does the hot gas cooling flow and the cool gas cooling flow correlate?
Yeah, I'm not sure I fully follow.
Okay.
How the cool, yeah. When you say the cool phase, you mean when the cooling flow kind of entirely cools out into a supersonic flow? Yeah, then it would just crash into this. Yeah,
maybe the question asker can unmute and clarify. I think, yeah. Well, all right. Or maybe clarify in Slack. And meanwhile, I'll have Joel ask a question. I can't hear Joel.
I could. So one of the things that I had a student try to do was look for flattening of X-rays in rotating galaxies, because one would think this would be easy to find, and actually it's very hard to find. You can always find some galaxies that are not perfectly spherical in X-rays, but so I'm wondering if angular momentum gets redistributed in the inner part. You know, one needs an effective viscosity, but there are magnetic fields. I mean, there are a variety of things. So that was one question. Let me ask the other question as well. I think this is mainly, well, it can be both observers and theorists. So the return of mass from aging stars in galaxies today, like the Milky Way, is almost equal to the star formation rate. And you know, when you add in 1 or 2 solar masses a year cooling from a halo, it exceeds the star formation rate. The implication being that the disk would be growing in mass and possibly size, depending on the angular momentum. So this seems like a question that, or a constraint eventually, that one can answer. And so I just put that out there to raise that issue.
Thank you. There's a question from Yakov Fairman. Cooling flow models or thermal balance models can both be used as baselines, with the other set of models being the deviation due to the presence or absence of feedback respectively. Where does the symmetry break? What can one set of models do that the other cannot?
Yeah. Yeah. I guess kind of the advantage, I wouldn't say advantage. Okay, the difference between the cooling flow model and the other models, like your model and like the precipitation regulatory model, is that the difference between the actual state of the gas in a cooling flow is the effect of feedback. Okay, so you can use a cooling flow to kind of learn how the hot gas has changed due to feedback. Okay, right. So because the cooling flow is just kind of this basic state of hot CGM. Okay, no feedback, you would get a cooling flow. So that's for me the difference, right? It's more like a conceptual difference. Okay, it's what would be like if I had a simulation which I was trying to understand what are the effects of feedback, like I do with fire. Okay, I just compare kind of the hot CGM to a cooling flow rather than comparing it to let's say Jakob to your model. Okay, then I know if your model is correct or not. But because your model has assumptions on feedback. Okay, it's different than cooling flow, which is just what you get without feedback. So I hope that answers the question.
Okay. Well, yeah. Does anybody else have a question for Jonathan or a question for Nir? We're 5 minutes to the end of our 2 hours. All right. Hearing no other questions, I want to thank you both and also make an announcement. There's going to be an after party tomorrow. It is the SZ CGM after party. And the time is, Ben, can you remind us of the time?
Yeah, 11 a.m. Pacific. So, and if I think I can confirm that. So that's right after the program tomorrow.
That's
so
an hour after.
What?
I mean, we finish at 10, so it's an hour after that.
Oh yeah, that's right. I'm sorry. Yeah, Mountain and there is a gap. Yes, thanks, Cameron. So yes, 11 a.m. is a gap. I was replacing Mountain and Pacific as I always do because they're 1 hour apart. So yeah, please do join that, and that's even better because you have a break for lunch or dinner.
Or whatever you happen to be.
Depending where you are.
Okay. So tomorrow, then, we have Dushan Karish giving us another keynote talk, this time a simulator's point of view on how does gas flow into galaxies. So until then, have a great time.
Thanks, everybody.
Very much.
Great job, Jonathan and Nir. Excellent tutorial.
Thanks very much. It's a pleasure.